Okay, great. So I think we're going to get started. So welcome back to the second plenary talk of NCNGT 2022. We're very excited to have Ina Petkova. Ina received her PhD from Columbia in 2012, where she was advised by Peter Oshvat. She previously held positions at MSRI, Rice, and Barnard before joining the faculty at Dartmouth College in 2016. She has received many awards, including the NSF Career Grant, and we're very excited to have her here to tell us about spectral grid invariants and Lagrangian Keyboardisms. But before she starts, I should have said this first. So for asking questions, we're going to ask that if people want to ask questions, you can put them in the chat and I'll monitor the chat and ask them to Ina out loud. And then also at the end, if you'd like to ask questions, you can use the raise hands feature and ask them out loud then if you'd like as well. So I think that's everything. And Ina, take it away.
All right, cool. Well, thank you all for having me. So I'm going to tell you about something new that we're working on, spectral grid invariants and Lagrangian Keyboardisms. Since there's no participants list and the expectation is there's a mix of kind of grad students and postdocs, a large number in the crowd, I just sort of assembled some random facts and basically feel free to take away whatever you want or just, make a list of buzzwords. If something catches your eye, then just go look it up after. So I'm not really, the goal wasn't to present a big result or anything, but more just exposed to a couple of subfields of topology through this. And so hopefully that gets accomplished. So this is work that's coming out of a summer program we just wrapped up at Dartmouth for undergraduates. And so the orange stars here for Mitchell Joubert and Noah Schwartz is that they're undergrads. So they're rising or already seniors at Dartmouth College. And this is also work with Zach Winkler, who's now a visiting assistant professor at Smith College, and with Mike Wong, who's spending the semester at LSU, and starting in January, he's going to be an assistant professor at U of Ottawa. Okay, so just a very, very coarse outline of what I hope to get through today is a couple of basics about contact topology, and mostly just within the framework of what I care about for today. So we're going to chat a little bit about three-dimensional contact manifolds, what are Legendrian knots inside them, and a concept of a certain kind of Keyboardism between those. So that's the first part. Then we're going to move on to introduce knot floor homology, which is an invariant of knots and links in three manifolds. So we're going to do it in a combinatorial, fairly approachable way. And so that's a good tool to study the kind of questions like the one we're going to pose. And we're going to wrap up with laying out some obstructions to the existence of the Keyboardisms we're going to talk about that come from knot floor homology. So that's the plan. Okay. So we want to study Legendrian links in one specific three manifold in R3, but just for fun, here's the definition of what a contact three manifold is. So if you have a three manifold M oriented, a contact structure in it is going to be a plane field in the tangent space for the manifold, which is totally non-integrable. Okay, so what this means is, one way to say it formally is I can write it as the kernel of a one form, so that this one form alpha is such that alpha wedge d alpha is everywhere non-zero. But even better, definition by picture, what this means that at every point of the tangent, at every point of the manifold, I pick a tangent plane in the tangent space. And non-integrable translates to the idea that nowhere, not even locally in my manifold M, could I find a surface so that the tangent space of the surface nearby a point fully agrees with the contact with these planes in C. So they kind of wiggle a little too much is the way to think about it. And so the example we're going to focus on today, which you could also take away as a local picture in general, maybe in a way, is R3 with the standard contact structure. And that is the kernel of dz minus y dx. So if you like, write it down and try to work it out. So what is the kind of kernel that I get? But I have the picture ready for you. And so what it looks like is we get horizontal planes everywhere over every point in the xz plane. But if we pick up a little bit of a y direction, so let's just focus on the y-axis itself, as you start coming out in that axis and the y-coordinate increases, your planes start to pick up a tilt. They start rotating about that axis a little bit. So as y approaches infinity, they attempt to get vertical, they never quite do. And same story as you go back. And so this picture, what you see on the y-axis is invariant in the x and z direction. So a fairly easy, maybe the easiest example we can think of. All right, and so what we're going to want to do is study Legendrian links. So a link in a contact 3 manifold is Legendrian if it's everywhere tangent to the contact planes. Okay, so maybe even though it's not a compact example, the simplest thing you can do here is say, hey, how about the x-axis? It's a good example. Okay. It's a bit much to try to visualize it sitting in space, and a lot of what we're going to do today is combinatorial. So we're going to think of these objects as in terms of what's known as their front projections or front diagrams. So you have that link floating around in R3. You're going to want to project it onto the XZ plane, except maybe I'm going to view it from the back of the page because I kind of like the X direction always pointing to the right. So if you focus on my baby example here, imagine that the y-coordinate increases as you dig into the page, into the tablet, and decreases towards you. So let's think about it then. I want my link to be, well, the link is everywhere tangent to the contact planes. So if we unfold it, for one thing, I can't possibly ever have vertical tangencies, right? I don't have vertical planes. So when I pick that perspective, staring from the negative infinity y direction, what I'm going to sort of see is these cusps. Maybe if I were to move my point of view, I would see that it's actually something smooth, but it's going to look like cusps in that projection. And I can also recover crossings. I don't have to think about them a whole lot because we said that these planes rotate here. So you can work out that things with higher slope are hiding behind strands with lower slope. Again, when you're looking from behind. So this is kind of annoying how I shifted my perspective here, but such is life. Okay, and so that's what the typical front diagram looks like. All right, so I do low dimensional topology, and that's math in dimensions 1, 2, 3, 4. So just for fun, let's kind of fill in the missing dimensions. So in 3D, we introduce a concept of a contact manifold with a Legendrian link in it. Now, let's go a dimension higher. So the counterpart of contact topology in 4 dimensions is symplectic topology. And so we're going to say that the smooth 4 manifold X is symplectic if it comes together with a differential 2 form, omega, which is closed and non-degenerate. We're not going to have to understand this a whole lot better than just like glance at a definition for today, but I wanted to have it out there for, again, hey, if I want to Google something after, here's a word to Google. And so if you have a symplectic 4 manifold, you can study certain surfaces in it. So a surface, a 2-dimensional submanifold is called Lagrangian if the restriction of your 2 form to it is 0. Okay. If you've never seen that stuff before, there's no reason you would have a whole lot of intuition what the hell that is, and that's fine. But maybe to just kind of connect the left and the right-hand side of this page, there's one very natural thing you can do. If you have a contact 3 manifold, so the contact planes are a kernel of a 1 form, then you can build what's called the symplectization of it. So you cross it with R, and your symplectic form is d of e to the t of that alpha times that alpha, where t is the R direction. Okay. And this is really just so I can have a cohesive definition of the main thing we want to study later, but we're not going to want to set it too well because we're going to actually study it with combinatorial methods, and you know, we can save internalizing this definition for another day. So main topic of today is that of Keyboardisms. So notice on the previous page, everything was L. Links were L, surfaces were L. So let's pass to lambda for links. So if we have two Legendrian links in the standard R3, then we want to ask what kind of cobordisms they may or may not exist between them. So we're going to look at the symplectization of R3. So think of any schematically of these planes as symbolizing R3, cross with R, like we said. And then we want to ask, when could I have an exact Lagrangian cobordism from the one link to the other? And what this means, definition by picture, is I don't know how well the dark green shows on everyone's screen, so I'm just going to retrace it with a highlighter. But the question is does there exist a surface of some genus, we'll get to that in a moment, so that for some high enough t, between that value and infinity, that surface just looks like a cylinder. It looks like the top knot cross t to infinity. And below negative that value, it also looks like a cylinder. The other link cross minus infinity to minus t. And in between, it does whatever it does. It's something compact. And there's a bit of a condition related to your one form. And so I want to ask that question, when can I find one of those? Okay. Okay, so how do we answer? This is just a very silly thing to write, but this is how it works in math overall anywhere, right? You want to answer cool questions, you need cool tools, right? And the harder the question is to answer, and the more you want to, well, I want to get something that's not already known, you kind of need something stronger. You need something more creative. And so we need fairly strong and good link invariants. But the more sophisticated they get, the harder they are to compute. So again, this is just a very, very kind of general mentality that we want to combinatorialize things like that and make them tractable, something we can compute, something we can understand. So let's dig in. So combinatorial. First of all, we're going to focus on
Can you go back a slide?
Not this one, I imagine.
Yeah, this one. So you're asking when, if you picked the, oh, sorry. So you picked lambda plus and lambda minus, and you're asking when does there exist a
So let me just make my chunk bigger. So I'm going to fix those. And I'm going to ask, maybe one dimension higher becomes darker green, but does there exist a cobordism for two fixed ends?
Great, thank you.
Thank you. Okay, so before I answer that question, well, I'm not going to answer it. I want to modify it and make it a little more comfortable. That's another thing we do as mathematicians, right? If I'm going to use whatever kind of tool, how do I want to rephrase the question so it suits what I can do? And so we're going to restrict to a special kind of cobordisms known as decomposable ones. And those are cobordisms that can be built out of certain basic pieces. And some of the basic pieces are, let's think on the level of these front projections, what happens? Well, topologically, it's just moving through time via a Legendrian isotopy. So you're isotoping the knot through Legendrian knots. But visually as a diagram, you can describe what you're doing in terms of an analog of Reidemeister moves known as Legendrian Reidemeister moves. So these are the first three. But you could also build up a surface. And so another thing you can do is you move through time. So it's very hard to see, but these kind of moves, they can go in any direction. So as time develops from bottom to top, you could go either way, from right to left, left to right, or the reflections of these moves. These remaining two, they're not really symmetric. So let me make this bigger. One of them is called a pinch, even though if you look at what it is, so suppose you have two cusps, you make them, they start getting closer and closer together through time until eventually you start creating a saddle. Okay, so it's kind of the opposite of pinch, a co-pinch. I don't know, maybe you're pinching through in here. And the other one is called a birth, which is you're creating a Legendrian knot from nothing. Okay. I said it's a special kind of cobordism, but we don't actually know if So if you allow the two ends, if they're both non-empty links, and if you require that your Keyboardism is connected, it's an open question whether all connected exact Lagrangian Keyboardisms between non-empty links could actually be decomposed. I can't give any intuition why that would be a yes or a no, but for the time being, our special kind may potentially encompass everything.
Does this question have an answer if we drop the exact condition?
I have no clue. Well, so I'm not a contact topologist to begin with, so I have no intuition on any of these things, and I don't even know the story. And so I had seen a version of this question that didn't even have the non-empty or connected condition. And someone just yesterday pointed out to me that that's not exactly the way you want to ask it, because there's counterexamples there.
Okay.
So I'm not answering your question, but the point is maybe look it up, let me know.
Okay, thank you.
Yeah. So let's get to it. First step, I'm going to want to represent links combinatorially. And so orange is my link. So I'm going to draw the link as a bunch of vertical segments. Going to throw in a bunch of horizontal segments to that. Almost looks like a link now. I'm going to make the vertical ones pass over the horizontal ones. And there you go. We're back to having a knot. So this is called a grid diagram. I'm really putting it on a grid. I'm making sure those vertical segments are spaced out. The horizontal ones are spaced out. So I'm going to build up an n by n grid by doing that. And you can draw every knot this way, every link this way. It's a fun exercise. If you've never tried it, sit down after at some point this weekend and try to show that that works. Okay, so now I have a very concrete way to draw a link. It's very algorithmic, systematic, whatever. Can I use that to compute various link invariants? Yes. And just as a warm-up example, it's not the one I want to talk about the most, but let's pick the Alexander polynomial just because we've all seen it probably in a different form as a different definition. And we're almost at an anniversary situation right now. So it was discovered in 1923. Let's give this talk again in a year. So given a grid diagram, I could get a Laurent polynomial in one variable is the simplest way to do it as follows. So I'm going to make a matrix. This is very dark, but that's almost because, like, don't read it. Just look at the picture. So I'm almost making it hard to see what it says. I'm going to put ones in every intersection point of that spacing things apart grid that I drew. And I'm going to put a 1 everywhere outside the knot. And then I'm going to start filling in the remaining spots. So what I would locally want to see, twist your head so the knot is kind of going upwards. And then you want to see one higher degree on the right side. So quick test for city, what should I put here?
Oh my God. Oh my God. Is it
Quick.
e to the -1?
Yeah, to the -1. I like it. Yeah.
Am I right?
All right.
Wow. Oh my God.
So quick one for Allison. What should I put here?
T.
I like it. And quick one for Martin. If I have a T and a T inverse without even looking, what could I possibly have here?
I hope a 1.
Yeah, good.
Yes.
So that's exactly how it works. Thank you, organizers. You've been amazing. And so I fill it in, I get a matrix. I'm going to want to take the determinant of that matrix. If I don't do anything, I'm running out of organizers. But what's the determinant I'm going to get here? Dylan is online, but he's muted.
How about a 0?
0.
I'm going to get a 0. Oh, that would be a tragic invariant. So I'm going to delete the right column and the bottom row to make life a little more interesting. I want to also point out before we calculate this, that this is really cool. If you look at what we filled in, at any point you see t to the n, that actually tells you how much the knot is winding around that region of the knot. Just kind of table that awareness for later. Okay, so we said we don't like 0 as a link invariant. And so I'm going to delete the last row and column, get a little more exciting, and take the determinant. There's another issue now. What if my grid was a little big? And so I'm going to divide by t minus 1 to the grid size minus 1, just to normalize things a little bit. And it turns out I'm going to get myself an invariant. Did anyone do the math here? So I did it because I tried doing it once in class, and I totally screwed it up. And so you should be getting t squared minus t plus 1 divided by t cubed here, I think. Okay. So that's my left-handed trefoil invariant in the following sense. So if I have two grids that represent the same link, and if I do the computation correctly, I should get the same answer up to possibly, I don't really care about it, an overall sign and multiplying by some power of t. And very cool. So I got something divided by t cubed that I don't want to think about the t cube. And it's really quick to do this computation for the unknot, make it sit in a 2x2 grid, and see that you get 1. And so trefoil and unknot are two different knots. That's a good start. Something cool just happened. Yeah, okay.
Can I ask a question?
Yeah.
Is the thing that procedure you described on the same side, like secretly a repackaging of the reduced Burrell matrix?
What's the Burrell matrix? Isn't that something from braids though?
Yeah, but like the grid diagram is like kind of Brady.
It's not too Brady to me.
I mean, I guess it's not Brady, but you can like go from that to your Brady.
Yeah. Does anyone know the answer?
The way I thought about it was via Fox calculus. I might also be connected to the Burrell matrix. I didn't think about it that way.
Yeah. Yeah, I don't know a direct connection.
Okay, thanks.
Anyway, I had never seen this definition of the Alexander polynomial until I saw grid homology, and I think that's how you guys figured that out, probably. Yeah, it's really cool. So let's get on with it. That's a great invariant, but it's not that great. There's a huge number of knots, infinitely many knots that all have trivial Alexander polynomial. This is not going to answer my big Keyboardism question. So I want to soup it up a little bit. I want to refine it. And get something more sophisticated that's going to answer deeper questions. And so maybe in a most black boxed way, around 2003, Ajvat and Sabo, as well as Jake Rasmussen, defined, given a link in a 3-manifold natural set of vector spaces, which I'm going to write as HFK hat, the simplest version of what they defined, indexed by pairs of integers, INJ. So that if you look at the dimension of each of these vector spaces, okay, and you take this alternating sum where you raise -1 to the power I and t to the power j. So that's called the graded Euler characteristic of the whole collection, or like the direct sum of all the vector spaces. You're going to recover the Alexander polynomial. But you actually get something a lot better. Okay. And the original definition is hard. You're doing some hardcore analysis in a high dimensional space, and it's exciting and it's awesome, but we're not going to do this today. Okay. So we're going to instead reformulate a little bit. So that reformulation is what now is called grid homology. And I guess it evolved. So the original definition was by Manulescu, Ajvat, and Sharkar, which addressed the simplest kind, this HFK hat. And little by little, it just like a matter of maybe months, a couple of more papers came out that tackled the more sophisticated versions of it and addressed things related to Legendre knots, and we're going to get into that, but that's why I'm writing greater than or equal. And apparently it's really easy to space out on time. This said 2007 until this morning, and then I realized that's wrong. Okay, so what's the story here? We're given a grid diagram, and from it, we're going to be able to construct a certain chain complex. We're going to keep life as simple as possible today, so complex over Z2, and its homology is going to be an invariant of the link, roughly. So it's going to get us this knot floor homology that we're trying not to define. Tensor a copy of two-dimensional vector spaces, Z2 plus Z2. How many copies is sort of instructed by the size of the grid and the number of link components in the link. But essentially, it gives us a way to recover knot floor homology itself. Okay. And so we're now in the second phase of the talk, I guess, where I want to define that stuff. And so the outline of this definition follows, and then we're going to go back to revisit Legendrian knots after that. Okay, so we have a grid diagram. We're going to get a little more careful now, and we're going to identify the very top and bottom of it, as well as the left and right edge. So now it's a toroidal grid diagram. And also, I don't want to keep drawing the whole knot because pictures are going to get messy. So I'm only going to keep track of the corners of the knot, like here. These corners, and I'm going to mark them as X's or O's in a way that the knot is always going to travel from X's to O's horizontally and from O's to X's vertically. Okay, so just replace with a slightly simpler picture now. Okay, same data, different drawing. Okay, so I want to define a chain complex, correct? So what are my generators going to be? There are going to be tuples of endpoints when I have an n by n grid. So I'm going to want to have 1 point on every horizontal line, also spread them out so there's one on every vertical line. If you're into combinatorics, you would think of that as well. I have permutations basically. Right, there's a lot of them. The one I highlighted, the set of white dots, is one generator. The set of these 5 purple triangles is yet another generator. Here it is. How many total on this picture? 5 dots for each generator, but I have 5 factorial ways to pick them, right? So many. And then if you have a 10 by 10 grid, you are like, oh, more undergrads, more coding power. But that's life. So that's your generators. What about the differential? Differential is also something really cool from the picture. We're going to count what's called empty rectangles. So we're going to say that a rectangle R, here's a rectangle on the picture. It just means something with boundary on the white lines. I'm going to say it goes from a generator X to a generator Y. If I see X at the bottom left and top right corners, I see points of Y at the top left, bottom right corners. And everywhere else on the picture, X and Y agree. All right. I can translate my point of view because I'm on a torus, but that's sort of what it should look like. I'm going to want it to be empty. So I don't want to see pieces of X and Y inside it. And I'm also going to want my rectangle to not contain X's and O's just for now. So like here's one example of a rectangle that starts at the white dots. And it would go to, I don't know, let's just draw some rectangles, to whoever disagrees at these 4 corners and agrees with the white dots everywhere else. And so you count all that stuff and you say, well, okay, these squares are, that new highlighted generator is in the differential of the white dots if I found that rectangle. And for the sake of time, I mean, I like to usually, I would pause and say, like, let's work this out together, but let's not. And so here's, plus we're in the generation where we just feed the data right away. Just kidding. And so here we are. So what's the differential of the white dots? It's a sum of 4 elements. Because like here's, for example, a rectangle, right? I'm on a torus, so I'm allowed to kind of cross. And so I have these 4 different rectangles, second one, third one, like that. Okay, so now we have essentially a complete definition of this chain complex. If you don't want to have the other details, hey, wasn't there going to be some pair of integers, I and j, so I can track the Alexander polynomial? Not for now, but we have a chain complex with a differential. This is a good start. Okay, maybe let's pause for just a second. I know we're waiting for questions at the end, but any questions so far? I know I tend to talk fast as well, and I'm just like showing a lot of stuff in a short period of time. And to repeat the disclaimer, the point is to just kind of trigger, like, here's some ideas, here's some constructions, they're really cool. Go look it up after and just kind of see glimpses of bits and pieces of stuff that I find fun. Okay, so now we've posed a question about Lagrangian Keyboardisms. We've seen the basics of knot floor homology in some form. So let's go back to Legendrian knots. So I could actually represent them by grid diagrams as well, if I'm a little careful how I should think of it. Man, 2006 was a good year. That's when I started grad school. It was awesome. So if you have a knot on a grid diagram or a link, you can actually naturally get a front projection for a Legendrian knot like that. So focus on a corner of the knot. I'm going to call it the northwest corner here, because it's at the northwest locally of where you see the knot going. So like this one is a southeast corner. And those two types, we're going to smooth them. Okay. And there's, that's about it. Two other types, the northeast and southwest corners. I'm going to just kind of see them as cusps. All right. Now I can't do this with a highlighter, but I'm going to connect and get the whole knot, and I'm going to rotate that picture 45 degrees clockwise. Okay. So like this. Almost looks like a front projection. Anything that bugs you about it?
Your crossing.
Crossings look screwed up, yeah. So it should be that the lower slope is in the front. So I'm just going to flip the crossings, and here's the end result. So whatever knot the grid was representing, the Legendrian knot I'm going to take is the mirror of that. Okay. So like that, we have some sort of correspondence. Well, I don't know, correspondence. So this is what I mean. If I have two grids that represent the same Legendrian link, then, well, they do so if and only if they can be connected by a sequence of well-understood moves. The first move is called a commutation. And what it does is you look at two consecutive columns. I've kind of drawn it very dark there, but if you see an X and an O in the one column, so that the X and the O in the other column are completely away from, so things kind of look, you can separate them by a line like that. Then you can swap the rows. And one way to think about it is here it kind of looks like I just did an isotopy. Sometimes it might be that you have an X and an O and another O and an X. And so maybe a knot is going like that. And maybe this sort of looks like a Reidemeister move of sorts and so on. I don't know. So that's a move you're allowed to do. And you're also allowed to change the size of the grid by what's known as a certain type of stabilizations or destabilizations. I'm not going to draw a whole picture, but imagine you have something zigzaggy and simple like this, and you could just sort of reduce to a straight line sometimes. So it's well understood when two grids represent the same link. Okay. And so if we have that, then we can ask, well, all right, anything exciting in grid homology that can tell me anything about these guys? And yes. So this is what's known as the Legendrian grid invariants. So we're back to this grid diagram, but we've just darkened it a little bit. And we want to focus on two special generators. This purple one is I'm going to take the upper right corner of every square that contains an X. And so I'm going to call this X plus, lowercase x plus. And it's a little ridiculous in the picture I picked because it's the same exact generator. Someone might already catch me in that, right? I'm identifying the left and right edges, but in general, not always. So you can also pick the lower left corners of the X's. And if you just pick a grid at random, typically that would be a whole different generator. But anything else that strikes you about these guys? What if I try to compute their differential? So I'm counting rectangles that have X plus at the bottom left and top right corner of it, and they're not allowed to contain big X's and O's. Yeah. But I picked them to be those corners. So I'm going to have some X. So the differential is 0 on those two, right? They're cycles. Cool. So I could talk about their homology class in grid homology. And it turns out that you get an invariant of the Legendrian link. So I don't know, depending what device you're using, this might be getting a little hard to read. But I'm going to use lambda in line with literature that defined these to denote these homology classes. Okay. Now, if you really want to make me not finish on time, you're going to pause me rightfully and say, what do you mean by an invariant? But let's just pause for a second and let's just not address that fully. I could ask things. I could say, hey, is it a 0 class in homology or non-zero? That's one cool thing I can ask about. Okay, so what about it? It's a good invariant. It's effective. So we've moved through time. It's a result of Oswald and Thurston that these two can distinguish Legendrian representatives of the same topological link, where the representatives have the same classical invariants. We didn't define them, but Thurston, Bennikin, and rotation numbers are two other invariants of Legendrian links that are really easy to define entirely from a front projection, easy to compute. And so these lambda plus and lambda minus could tell us new stuff. Okay. Well, okay, what about Keyboardisms? So forward in time, Baldwin, Lidman, and Wong in 2019 told us that we could actually use these to study Keyboardisms as well. So here's maybe the most, the tersest way we can formulate something is suppose, let's focus on lambda plus. Suppose you have two grids, lambda plus for one is non-zero, lambda plus for the other is 0. Then you could not have a decomposable Lagrangian Keyboardism that is built up from the guy with the non-zero invariant at the bottom going up to the guy with the 0 invariant to the top. And in a few minutes, I'm going to give a glimpse of why that is. But just for fun, because I want to just discuss something a little more is, well, can we generalize this? Can we get even more abstractions? Okay, and also because I want to dump more math concepts that I wasn't necessarily too familiar my first year grad school. So here they are. We actually could study a slightly more exciting version of grid homology, which is a filter chain complex. So this is not anything new. It's just also in the original grid homology papers. So first step is I'm going to modify the differential. I'm going to this time allow to count rectangles that contain x's as well. So these are in red. We had these 4 rectangles before. Now I have 2 new ones that are also allowed, starting at the white dot, this one or this one. So I've changed the differential for good or bad. Am I going to get something better or not? I don't know, but I've changed it. Second thing I'm going to do before I tell you what a filter chain complex is I'm going to actually go back to what were those pairs of integers I and j that once I take the Euler characteristic, I recover the Alexander polynomial. I have just for fun, and if I don't know, there's a place to upload slides later. I have just for fun a self-contained definition, but let's not go through it. But by looking at the picture for the knot, at the grid diagram, I could define 2 quantities for each generator, known as the Maslov and Alexander grading, just by counting something. Okay, and so each generator comes together with a pair of these, with a pair of numbers. And so now I have a new differential and I am paying attention to the grading. And with that information, I can make a filter chain complex and study it instead. So first point, if you actually process what the definition of the bigradings is, you would come to realize that if you have an empty rectangle that might contain some x's but no o's inside it, from a generator x to a generator y, like that, then the Maslov gradings are off by 1 for these two generators. And the Alexander gradings differ by the number of x's in the rectangle. So what this is telling me is that this new differential, which I denoted as delta tilde sub O, because O is the forbidden point now, it either preserves or lowers the Alexander grading. Okay. So I can get myself a filtration. It induces what's known as a filtration on a chain complex, like this. So I could basically nest up my chain complex. In our case, everything is bounded. But I could look at this whole chain complex and say, FT is going to be the entire subcomplex generated by things that are in Alexander degree up to T. Okay. And so if I allow to only look at things within Alexander degree up to I, whatever space those generators span, it's an actual subcomplex because of this fact right here, right? Because the differential cannot increase. And so I could filter by using the Alexander grading. I have finitely many generators. Eventually, I'm going to run out and just get to 0. Okay. And if you think back, originally we were not defining, we were not allowing any x's in the rectangles. And so if I take what's known as the associated graded space for that filter chain complex, which is if I take successive quotients, I'm kind of selectively highlighting here, then the induced differential on that is exactly what counts rectangles with no x's or o's in it. And so that would give me a different way to recover grid homology. Okay. Fine. What else do filter chain complexes do? They induce spectral sequences. And I'm just going to say that very quickly, but my goal is to wrap up in the next couple of minutes without actually fully defining spectral sequences right now and do something else instead. But if you've seen that kind of stuff, then you would realize that if you have a filter chain complex, then you get a spectral sequence from the homology of that associated graded space to the homology of the total complex. If you want to black box a lot of that, then let me just say that you get a sequence of chain complexes indexed by integers. So complex EI with a differential delta I, and you get a sequence of these somehow. So just to be able to state something and define something, let's keep it at that. Okay, so remember we had this element x plus. There was going to be the top right corners of x's on the grid. And I could consider its homology class in the grid complex. Well, surprise, the first page of the spectral sequence was going to be the grid complex, right? So I could consider its homology class, and we call that lambda plus. Now I'm going to slightly change notation and call it lambda plus sub 1 to keep track that that was on the first page of the spectral sequence. And for a little while, I may be able to keep doing similar things and say, okay, now this element on E1, when you have a page of a spectral sequence, you can take its homology. That would give you the generators of the next page, and it would also induce a differential on the next page. I'm black boxing it, but let's just say, suppose that you know the delta I of this lambda I, the previously defined lambda, suppose it's 0. Then I can talk about the homology class of this lambda I on yet the next page, EI plus 1. And if I can talk about it, then I'm going to call it lambda I plus 1. Okay. Maybe sometimes at some point I can't keep talking about it. And so the first time that this happens, at whatever page I it happens, I'm going to label that as n plus of g. some numerical invariant of when things stop working out this way. And if I can keep doing it, I'm just going to say that this n plus is infinity. Okay. So I'm essentially reformulating things that, if I can do some advertising, what I think is like the best thing to use for undergrad projects about grid homology is this grid book. And so it's all kind of hidden there. It's just encoded slightly differently notationally and the way they formulate things. But the fun part for today is that you actually get a sequence of invariants that can obstruct Lagrangian cobordisms as well. Okay, so right, we get all these lambdas, one for every page potentially, and we get these n pluses, or similarly lambda minuses and n minuses. Now, there's a lot written here, but suppose again you have a bottom link lambda minus and a top link lambda plus. If pick your bottom left or top right generator, whatever. If the n invariant for the bottom guy is bigger than the one for the top guy, or if at some point you hit a lambda I that's 0 for the top link, but is non-zero for the bottom link, regardless at which page it happens, if any of these things happen, then you have obstructed the existence of a decomposable Lagrangian cobordism from lambda minus to lambda plus. So kind of think of it as an analog or a bit of a generalization of the previous result that we mentioned by Baldwin, Lidman, and Wong. Okay. And maybe just to wrap up, why is that theorem true? So what do we show, or what is the way that Baldwin, Lidman, Wong do it? Same principle. In the language of filtered complexes, what we do is we're going to show that there's some homomorphism. Map on complexes going the other way. And because I said that I don't want to discuss spectral sequences, and also to just kind of say when we code this up, we do it in a slightly different way. Here's a fact. You can tell if n plus is finite. Suppose it's a number I. So that was when you stopped having that delta I of lambda I is going to be 0. So you can't talk about its homology class on that page anymore. Turns out that's exactly at the smallest I, for which the boundary of your class X plus is non-zero. When you look at the homology of a certain quotient of the filtered complex, where you're quotienting things in degree a minus 1, is the degree of your generator, by things in degree up to a minus I minus 1. And similarly, you can kind of analyze when is lambda I 0 or non-zero by thinking about the class of your original element of the grid complex as something in a quotient homology. What you're really doing is you're asking, hey, if I can count rectangles that have this many x's in it, I could answer that question. So I'm going to say I'm going to count rectangles with up to 5 x's. Then I'm going to count up to 6 x's and do that step by step. You could computationally approach things that way. So I think it's kind of cool. There's a little bit of math to prove that it works out this way, but once you do it, it's just fun. And so the reason the obstruction is an obstruction is that we show that if there is a cobordism from a lambda minus to a lambda plus, then there is a filtered chain homomorphism for those filtered complexes going the other way that behaves nicely with respect to these special generators. And I don't want to go too much into what nicely means, but it's what it takes a generator to the corresponding one plus things that don't matter. Maybe they're in lower filtration level and so on. Okay, that's approximately how you prove this. And just to wrap up, all right, so what? We want examples. Otherwise, well, otherwise that's still cool, but we want examples. So can we find examples where maybe you can obstruct cobordisms by n or by lambda I that's not lambda 1, the one we already had, so that lambda 1 does not obstruct. And you can ask, well, can I do it for genus 0, 1, 2, 3, and so on? We don't yet have examples for positive genus. What I should have mentioned is that unlike the smooth setting, the genus of your exact Lagrangian cobordism is fully prescribed by these classical numbers, the Thurston, Banneken, and rotation number. So you can't mess with that. It's just what it is. And the rest is, can I make the geometry work out or not? So we're running examples on some server as we speak, and maybe something more exciting comes out. But in the case of g = 0, yeah, there's an example. So if you look at the pretzel knot -4, -3, 3, there's 3 different non-destabilizable Legendrian representatives, which just notationally here I have as lambda 1, minus lambda 1, and lambda 2 here. All their lambda 1 invariants are non-zero, both for the plus and the minus generator. However, these n plus and n minus quantities differ, and that was how far along the spectral sequence you could keep talking about homology classes. And so you can infer various relations, that there's no cobordism from any of these left guys I've listed to the right ones. So this is basically, this first one was proved by Gola and Juhas as well, by a computation of this delta 1 of lambda 1, for example. Yeah, so we're hoping for more examples in the near future, but I'm just going to stop here. Thank you.